Now that we've had some practice working with double integrals in both rectangular and polar coordinates, we'd like to look at some applications to these double integrals, which leads us to surface area and parametric surfaces. So I begin here with a remark that's going to tell us how we're going to compute this surface area. Let sigma be a surface of the form z equals f of xy. And let me pause here already and make sure that when you're computing this surface area, that you're in the correct format where z is solved for explicitly. And let's suppose that this surface is defined over a region R in the xy plane. Assuming that f has continuous first partial derivatives, the surface area of sigma over R is given by the double integral over R of the square root of the sum of the partial derivative squared dA. Now, I just want to note that this is the arc length formula exactly if you'll just note that this extra factor of 1 is partial z quantity squared. So really all we're doing is we're taking the partial derivatives in each coordinate, squaring them and adding them up and taking a square root. The only difference is we're adding another iteration of an integral. So instead of taking an arc length, when you do it twice, you get that two-dimensional aspect, giving us a surface area rather than an arc length. As always, when we're working with these arc length and surface area formulas, you really have to work hard to simplify underneath the radical so that what you're working with is integrable. Remember that you really need to simplify in order to either eliminate the square root entirely or get it down to something where you can do a u substitution. All right, let's take a look at our first example. Express the area of the given surface as an iterated double integral and then find the surface area. All right, so we have the portion of the surface z equals 2x plus y squared that is above the triangular region with vertices as listed. All right, so before I do anything, let me go ahead and just sketch the region that we're integrating over. So we have the origin 0, 1, and 1, 1. So I'll go ahead and sketch that triangular region. Here's our region R. And then we get to make a choice here of whether we want to take vertical or horizontal slices. We could actually do either way. However, I think horizontal slices are going to be easier just because one of those boundary lines then is going to be x equals 0 on the left side. And of course, the other side is y equals x, which maybe I'll write as x equals y. And again, that always sounds silly to write it that way, but we actually want it written as x as a function of y. And then where are we going along our y-axis? The smallest y is 0. The largest y is 1. All right, so let's go ahead and compute our partial derivatives. I'm going to notice here that my function or my surface is already in standard form where z is solved for explicitly. So partial z partial x just gives me the constant 2. And partial z partial y gives me 2y. And then of course, partial z is just 1, which is where we get that extra factor of 1. All right, so let's go ahead and set up our surface area integral. I'll come back for those limits of integration, but first, I have my square root of del z del x squared, which is going to be 4, plus del z del y squared, which is a 4y squared, and then of course plus 1. And then my dA, I need to decide, do I want dx dy or dy dx? And so if I look back at my horizontal slice, my thickness is in the y direction. So that tells me that my dy differential will be on the outside, which leaves my x differential on the inside. All right, notice also that this is a good choice because as I have my integrand written, I don't know how to integrate it with respect to y right now. So I'm hoping that by integrating with respect to x first, that it will become more clear how we're going to carry out the integration. All right, now let's go ahead and do the outer limits of integration. Y is ranging from as little as 1 to as large, or as little as 0 to as large as 1. And then X on the rightmost line, I have X equals Y, and leftmost is X equals 0. So I've set up my double integral here. I can, of course, just do one simplification, adding the constants together, which gives me a 5 plus 4y squared. All right, so now since I'm going to integrate with respect to x first, I don't see any x's. So I'm just going to tack an x onto my integrand. And I want to evaluate from x equals 0 all the way up to y. All right, so when I plug in 0, this entire thing is going to drop out. So I need only plug in for y. So I have the integral from 0 to 1 of y square root of 5 plus 4y squared dy. All right, and I'm much more satisfied with this integrand now for integrating with respect to y, because now that I have that extra factor of y outside, I can follow through with a u substitution. So I'll sneak that in over here. U equals 5 plus 4y squared. Du is a 2y dy. So y dy is a 1/2 du. Now, I will also go ahead and change my limits of integration by taking these y limits and plugging them into my u equation. All right, so I won't even show that work. I'll just kind of talk through it aloud. All right, when y was 0, when I plug it into the u equation, I get 5 plus 4 times 0 squared, which is 5. And when y was 1, u becomes 9. All right, and then I get my factor of 1/2. Everything beneath the radical becomes a u, and I'm going to write that radical as a 1/2 power du. And now I'm leaving the y variable behind. I'm never going to resubstitute since I changed my limits of integration. Let's go ahead and carry out my derivative. Oop, and I just noticed a mistake. Let's go ahead and fix that. This 2y should have been an 8y. So we have 8 here, 8 here, and 8 here. Okay, my apologies for that error. And now let's go ahead and integrate. So I have 1/8. When I raise the power by 1, it becomes a 3/2 multiplied by the reciprocal is 2/3 u to the 3/2 power, where u is ranging from 5 to 9. So I get a 1/12 u to the 3/2 power. All right, so applying the fundamental theorem of calculus, I get 9 to the 3/2 minus 5 to the 3/2. Technically speaking, I would give you full credit right here. However, we can reduce 9 to the 3/2 power. That's the square root of 9 cubed minus the square root of 5 cubed. Square root of 9 is 3. 3 cubed is 27. So I have 1/12 27 minus 5 root 5. All right, so there's our final answer, but I will also box in this previous answer. If you didn't want to simplify your 3/2 power, that would have been fine as well. All right, so this example was computed completely in rectangular coordinates. Depending on what your region looks like, if your region of integration is a polar region, then it may be beneficial to switch to polar coordinates like we learned about in 14.3. So that leads us to our next example. Express the area of the given surface as an iterated double integral and find the surface area. Before we even get started, I just want to make a note here at the bottom that there is more white space on the next page. Whoops. So we'll use this white space at the bottom of page 1 just for our setup. and then we'll carry out the actual integration right down here. You can see all this nice white space on page 2. All right, so what are we looking for? We want the surface area of the portion of the sphere, and you can see that sphere has radius square root of 8, that is inside the cone. Z equals the positive square root of x squared plus y squared. So I just want to emphasize here, instead of the double cone where we have a cone heading up the positive z-axis as well as down the negative z-axis, this is just the positive square root. So we're only getting the upper cone. Let's just sketch this surface to begin with. So here's X, Y, Z. All right, we have our sphere. And then we also have a cone. Maybe I'll note that this is radical 8 in every dimension. All right, and then our cone begins at the origin and emanates outward. Now, this is not going to be a super accurate sketch, but it's just a sketch nonetheless, just to identify what we're working with. So we see some intersection here. And of course, this cone is infinite, so this cone just keeps going up. All right, but let me highlight what we're working with. We want to find the surface area of the portion of the sphere inside the cone. So let me grab a bright color here. We're looking for the surface area of this polar cap at like the North Pole of the sphere. All right, so we can see that. Now, what we'd like to do is when we're calculating this surface area, we need to identify the region over which we're integrating. So if we carried this down to the XY plane, what would it look like? So if I just shone a light down or was looking at a bird's eye view, if I stomped on this cone, it would flatten to a circle in the XY plane. Now, it's not all the way out to that square root of 8 radius, right? And in fact, we're not sure what the radius of that circle is. So that's our next step, is to find out what is that line of intersection between the cone and the sphere so that we know what our region of integration is going to be. So whenever we're looking for intersections of curves or surfaces or anything of that nature, what we want to do is we want to eliminate a variable. So I'm going to take the sphere and I'm going to solve for z. So z squared is 8 minus x squared minus y squared. Now, normally when I would square root, I would square root both sides. But here, or I shouldn't say square root both sides. I would square root both sides, but I would take a plus or minus. Here, we actually only care about the upper hemisphere. So I'm going to intentionally only look at the positive square root. And then, of course, I already have z solved for in the cone. And so I'm going to equate this z with this z. So let's do that next. I get the square root of 8 minus x squared minus y squared equals the square root of x squared plus y squared. So squaring both sides, I get 8 minus x squared minus y squared equals x squared plus y squared. So 8 equals 2x squared plus 2y squared. And finally, x squared plus y squared equals 4. So now we see that indeed that is a circle. That line of intersection is a circle up at the polar cap. And furthermore, it is a circle of radius 2. So I like to draw my projection onto z equals 0, that is the xy plane. And the projection of this surface looks like a circle with radius 2. All right, and this is what we're calling our region of integration R. Now, the moment you see that your region is a circle, that is indicative that polar coordinates are going to be useful in this circumstance, because actually integrating over a circle in rectangular coordinates is quite painful. What you're going to be dealing with is a bunch of these square roots of 4 minus x squared and negative square root of 4 minus x squared, et cetera, et cetera. But if we instead change it to polar coordinates, we're working with things like 0 to 2 pi and a radius from 0 to 2, and our limits of integration become much simpler to work with. So again, whenever you're working with circles or annuli, in other words, rings with the circles with the middles cut out, anything of that nature, that means you should be working with polar coordinates. All right, so remember, we had just determined that z for our surface, we're going to consider the positive square root of 8 minus x squared minus y squared. And of course, you can rewrite this as 8 minus x squared minus y squared to the 1/2 power. Now, to set up our surface area integral, we need to calculate the partial derivatives, del z del x and del z del y. So let's start with del z del x. I'm going to use the chain rule. I'm going to pull the 1/2 power down in front, leave the inside, and subtract 1 from it. That's going to give me a 1 over 2 square root of 8 minus x squared minus y squared. And then the chain rule will have me multiply by the partial derivative of the inner function with respect to x, which gives me a negative 2x. Now, of course, here I can cancel the 2 on top and bottom. And so my partial derivative is negative x over this radical expression. By symmetry, we can see that the partial of z with respect to y is going to be almost identical, with the one difference that on top I'm going to have a negative y. All right. So now we're ready to set up our surface area integral. As always, I'm going to leave my limits of integration for last. Remember that surface area integral was the giant square root of all the partial derivatives squared and added up. So when I square these things, thankfully, those square roots are going to cancel. I get x squared over 8 minus x squared minus y squared plus y squared over 8 minus x squared minus y squared. And then, of course, I always have my plus 1. And then I have my dA. So now we'd like to look at this and we say, well, gee, that looks really rotten inside. Let's go ahead and simplify as much as we can. The first thing I'm going to do is I'm going to combine these two first fractions since they already have a common denominator. And we'll come back to this region here in a moment. So I have an x squared plus y squared over 8 minus x squared minus y squared. And then remember this 1 right here? I'm going to rewrite it with that common denominator. So I'm going to write that as 8 minus x squared minus y squared over 8 minus x squared minus y squared. All the while we have this dA tacked on at the back. So now that I have all of my fractions with a common denominator, I can combine and I see my x squareds cancel and my y squareds cancel. And this entire double integral here with the inside collapsed to this single expression under the radical, which is 8 over 8 minus x squared minus y squared, dA. All right, so we discussed that our region R was a circle, which is a simple polar region. And furthermore, whenever I see piles of x squareds and y squareds that are either both being added or both being subtracted, that just screams to use polar integration because I can swap those for r squareds. So let's go ahead and make the switch from rectangular to polar coordinates. For my integrand, the constants are the same. And on bottom, that becomes an 8 minus r squared. dA is always r dr d theta. And now let's talk about our limits of integration. Our radius is ranging from 0 to 2. Remember that 2 is coming from this projection diagram right here, where our intersection circle had a radius of 2. And then our theta, we want to go all the way from theta equals 0 all the way back to theta equals 2 pi. So since we want the full circle, not a quarter circle, not a semicircle, we want the full rotation 0 to 2 pi. All right, we're finally ready to carry out our integration here. And we notice that we're going to have to make some sort of a substitution. And what I'm going to substitute for is 8 minus r squared. I'm choosing this because I know that when I take the derivative, I'm going to get a single factor of r, which is going to cancel out with that r at the back end. So if u is 8 minus r squared, then du is a negative 2r dr. And so again, we can say that r dr is a negative 1/2 du. And by the way, if you want, you can write this as a square root of 8 over a square root of 8 minus r squared, and then just delete this overarching square root. And that's going to simplify a few things here, because the square root of 8 is just 2 square root of 2. So I'm going to note that here in my next step. I still have my theta limits from 0 to 2 pi. I'm going to go ahead and change my r limits in terms of u. So I'm looking at this u equation. When r is 0, u is 8. And when r is 2, u is 4. So I've just changed my limits of integration. I had my square root of 8 on top, which is a 2 root 2. And then I had my square root of 8 minus r squared, which becomes a square root of u. And my r dr became a negative 1/2 du, and then d theta. So I'm going to cancel my 2's on top and bottom. I'm going to rewrite this as the integral from 0 to 2 pi, integral from 8 to 4 of negative square root of 2 u to the negative 1/2 power. All right, so now we're ready to integrate. When I integrate this, I'm going to add 1 to the exponent, which makes it 1/2, and then multiply by the reciprocal of 1/2, which of course is 2. So I have a negative 2 root 2 square root of u, where u is running from 8 to 4 d theta. And so what I get here is negative 2 root 2. The square root of 4 is 2. And the square root of 8 is 2 root 2. All right. And then, of course, we're integrating with respect to theta. And so now this is all just a constant. I think I'll go ahead and just distribute this expression here. So if I distribute the negative 2 root 2, I'm going to have a positive 8 minus 4 root 2. And then when I integrate with respect to theta, there were no thetas. So I'm just going to tack a theta on and evaluate from 0 to 2 pi. And so my final answer here is 8 minus 4 root 2 times 2 pi. And we just made it. All right, so again, that was an example of computing surface area utilizing polar coordinates to our benefit. Whenever we're doing problems like this, we want to keep in mind the relationship between rectangular and cylindrical coordinates. So I have those listed. And we're also going to start working with spherical coordinates. So I've listed those relationships here as well. So what we'd like to do next is use those relationships to express surfaces parametrically that are given in rectangular coordinates. So for this first example, I want to find a parametric representation of the surface in terms of the parameters u equals x and v equals y. So we have 14b here. I'm going to start just by stating u equals x, or in this case, x equals u, and v equals y, or y equals v. And so how can we then express z? All right, so as an intermediate step here, I'm going to look at my original equation and I'm going to say, okay, well, 3z equals y squared minus 5. So z equals 1/3 y squared minus 5/3. So now I don't want to express z in terms of y, but remember y was v, so I can write z as 1/3 v squared minus 5/3. And this is our parametric representation of that surface. All right, so let's go a different route. Let's use cylindrical coordinates to represent a surface parametrically. So what we want to do is we always want to come up with equations for x, y, and z because we're starting in rectangular coordinates. So how are x and y related to r and theta in cylindrical coordinates? Well, x is our cosine theta and y is our sine theta. Now in cylindrical coordinates, z is just z. There is no change in that coordinate. However, the directions specifically said that they want it in terms of r and theta. We don't want any z's involved. So we need to come up with an expression that relates z to r and theta. And so if I look back up at what my definition was for z, I can plug in what I have for x and y. So this becomes r squared cosine squared theta minus r squared sine squared theta. And you could absolutely leave your parametric representation like this, or you could factor out an r squared and then leave it as a cosine squared minus sine squared. All right, so here is our parametric representation of the surface z equals x squared minus y squared in terms of r and theta. And of course, we wouldn't like to leave out spherical coordinates here. So let's do an example that's utilizing spherical coordinates. All right, describe the cylinder x squared plus y squared equals 9 in theta and phi in spherical coordinates. All right, so I want to make an important observation. Notice that phi is not listed. Spherical coordinates is typically in terms of theta, phi. Oh, excuse me, not phi. Phi is listed. Rho is not listed. Here we go. Spherical coordinates are typically listed as rho, theta, phi, but they want us to express this surface just in terms of theta and phi. So we don't want our parametrization in terms of rho. Now, our standard coordinate system for spherical coordinates is x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. So our goal is to get rid of rho in each of these coordinates while somehow using the relationship that x squared plus y squared equals 9. All right. So first of all, what is x squared plus y squared? All right, that is rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. And what we can do here is we can factor out a rho squared sine squared phi. And then in that case, it's going to leave us with cosine squared plus sine squared, which we know to be 1. So this whole thing reduces down to a rho squared sine squared phi. And then remember, what did x squared plus y squared equal? It equaled 9. All right, so keeping that in mind, what I can do then is square root both sides. Again, normally I would be very careful with the plus or minus, but we always assume that rho is positive. So if I square root both sides, I get that rho sine phi equals 3. So let's go back up to our coordinates here. I see a rho sine phi and a rho sine phi. Those can be immediately replaced with 3. So let's do that first. X equals 3 cosine theta and y equals 3 sine theta. And now we look up at our z equation and we don't have a rho sine phi, we have a rho cosine phi. So what I'm going to do is I'm going to solve for rho here. Rho equals 3 over sine phi, assuming sine phi is non-zero. And so then I can replace my z with 3 divided by sine phi times cosine phi. And of course, this reduces to a 3 cotangent phi. And I have successfully expressed my cylinder in terms of spherical coordinates only involving theta and phi. All right, so we've done 3 practice problems of rewriting rectangular surfaces parametrically. And what's the point, right? Why are we worrying about doing these things? Well, as it turns out, we can work with finding surface areas of parametric equations. And in my opinion, it's a little bit easier doing it in that format. So first, let's talk about how to find a normal vector to a parametric surface. If sigma is the graph of R in terms of U and V, and if the cross product of the 2 partials of R is non-zero at a point, then the principal unit normal vector to the surface at that point is denoted by n, or n as a function of u and v, and is defined by the cross product of those 2 partials divided by the norm. Now remember, this is the principal unit normal vector, which is why we're dividing by the magnitude to make it of unit length. I have a remark immediately following that says, look, if we're just finding equations of tangent planes or things where we need normal vectors, who cares if it's unit or not? We just want a normal vector. So you can take any scalar multiple of this principal unit normal vector, and that'll suffice for a normal vector. So typically, we're going to just leave off the division by the magnitude and just work with the cross product of those 2 partials. All right, so our next example, we want to find an equation of the parametric or of the tangent plane to the parametric surface at the stated point. All right, so remember, when we're trying to find an equation of a tangent plane, we always want to take our normal vector, dot it with r minus r naught, and equate it to 0. All right, and this is where r naught is the vector from the origin to the point in question. So we can find this point by evaluating r at the given values of u and v. So let's go ahead and find r of 1, 2. So that's going to be 2 in the I hat, -1 in the j hat, and 3 in the k hat. So I'll just note here my point. All right, and so I'll use this as my vector R naught. All right, next we need a normal vector. And so that's what our definition and later remark was telling us. What we want to do is we want to find the partial derivatives of R and then cross them. So let's start with partial R, partial U. All right, so when I'm taking the partial with respect to U, the derivative of UV is just V. And then the other two coordinates give us 1. Now I specifically want this partial when U is 1 and V is 2. So that gives me 2, 1, 1. And similarly, del R, del V is U, negative 1, 1. So when U is 1 and, whoops, I just noticed that I wrote that incorrectly up here. V equals 2. I get out 1, negative 1, 1. All right. So finally, for my normal vector n, I want to cross these two partials. Now remember, the cross product cares about the order. So del R, del U cross del R, del V is the opposite or the negative of del R, del V cross del R, del U. But it really wouldn't matter here because we're trying to find a normal vector. So whether we take a normal vector pointing one direction or its opposite, it's still going to be normal. So the order of your cross product really is unimportant here. I'm going to set up my cross product by way of determinants and throw in my vectors, 2, 1, 1, 1, negative 1, 1. And then carry out the cross product. We've been doing this for several chapters, so I won't show my work here. So in the I hat coordinate, I get 1 minus a negative 1, which is 2. In the J hat coordinate, I get 2 minus 1 is 1, but we have to negate that. And then in the K hat coordinate, I get negative 2 minus 1, which is negative 3. All right, so finally, plug it into that formula that I have up above, n dot R minus R naught equals 0. So 2, negative 1, negative 3 dotted with x minus the x coordinate of my point 2, y minus negative 1, which becomes plus 1, oops, and z minus 3 equals 0. And I'd like you to at least take it one step further. This is 2x minus 4 minus y minus 1 minus 3z plus 9 equals 0. And I'll put it into standard form, 2x minus y minus 3z equals, let's see, I would have a positive 4 on the left. So when I move it over, a negative 4 on the right. All right, and there's our equation of our tangent plane. We have one more example to round out this section here. So remark, let sigma be a parametric surface whose vector equation is given by R as stated. Then the surface area of sigma over the region R in the UV plane is just the double integral over R of the magnitude of the cross product del R del U and del R del V dA. All right, so again, just kind of coming full circle, we'd like to compute surface areas. And instead of computing a surface area when our surface is given in rectangular coordinates, we're now going to compute it when it's given parametrically. All right, so our final example, find the area of the given surface. We want to find the area of the portion of the cone, as defined here, for which U and V are bounded by those inequalities. The nice thing about these problems is sketching the region or the surface is less important because your limits of integration are basically given to you, right? These inequalities are going to provide your limits of integration. One thing that I'd like to point out here right out of the gates is that the boundaries on U are in terms of V. That's very important. Whereas the limits on V are constant. That's going to determine the way we're going to integrate this function. I want to integrate with respect to u first so that when I plug in those limits of integration, they're non-constant and leave everything in terms of v, and then finally integrate with respect to v last. So that's one thing that I notice right out of the gates. Next, let's go ahead and find those partials so that we can set up our integral. So I'm going to compute del r del u first and foremost. That's going to give me a cosine v, a sine v, and a 1. And similarly, I'll find del r del v. That's going to give me a negative u sine v, a u cosine v, and a 0 there in the third component. Next, I'd like to compute the cross product since that's part of my integrand. All right, so I have a cosine v and a negative u sine v. In the j hat component, I have a sine v and a u cosine v. And in the k hat component, I have a 1 and a 0. All right, so what do we get here for this cross product? In the I hat, I get 0 minus u cosine v. In the j hat, I'm going to go ahead and stick my negative out there. I get a 0 minus a negative or plus u sine v. And in the k hat, I get a u cosine squared v minus a negative or plus u sine squared v. All right, so I can drop all my zeros. I have a negative u cosine v. All right, and then here it looks like I have a negative u sine v. Let me make sure if that's correct. So let me get red. If I strike through this row and column, I get 0, 0 minus a negative becomes plus. But then when I gate it, it's negative. All right, just wanted to make sure that that's correct. Whoops, let's go back to black. A negative u sine v. And then finally, when I factor out a u, I get a cosine squared plus sine squared reduces to 1. All right, and then here in the end, what I'm going to do is I'm going to find the magnitude of this cross product using the distance formula. So this is the square root of u squared cosine squared v plus u squared sine squared v plus u squared. Again, these first two terms, you could factor out a u squared, and the cosine squared plus sine squared is 1. So this becomes the square root of u squared plus u squared, which is the square root of 2u squared. In this case, I would write this as the square root of u times the absolute value of u, but remember our bounds on u are from 0 to 2v. So we already know that u is positive. You can drop those absolute values. All right, so now we can finally set up our surface area integral. I'll set up my limits of integration second, but let me first just set up the inside. I'm taking the square root of 2u dA. And then we had discussed that we could either set this up as a du dv or a dv du, but because our limits of integration for u are in terms of v, we would like those to be on the inside. So we're going to run u from 0 to 2v. And let me just indicate then that I'm going to integrate with respect to u first. And then dv is at the end, and that's running from 0 to pi over 2. So let me zoom back in here. All right, and we'll integrate with respect to u first. Rewriting my first integral, I have the square root of u over, or the square root of 2 over 2 u squared from 0 to 2phi. dv. And so this is the integral from 0 to pi halves of root 2 over 2 times 4v squared. Whoops, no parentheses there. 4v squared dv. Cancel a 2 on top and bottom, and then of course integrate with respect to v. This gives me a 2 root 2 over 3 v cubed from 0 to pi halves, which is 2 root 2 over 3 pi cubed over 8. And so I can cancel a 2 on top and bottom. And my final answer is the square root of 2 pi cubed over 12. All right, this concludes our lesson over 14.4, parametric surfaces and surface area. And up next, we're going to introduce triple integrals, and we'll stay in triple integrals for several sections then.